I just orient the right way. Yeah. All right. So let's talk about that formula that you used on, or will use in the vibrating string lab. I have a string here with a uniform linear density of mu. Linear density, mass divided by length. And since if I took a small little piece of it, that would be equal to dm dx, since the length is in the x direction. And so we will come back to that. Something just to sort of keep under your hat for the moment. As we send the pulse on it, so I got the long coil there, or long string, and I put a pulse in it, we have a wave that is traveling to the right at some speed v. The wave is traveling dx dt. dx dt. And so at this moment in time, if the wave is traveling to the right, this part of the string is going up, this part of the string is coming down. In terms of the linear density, we are assuming that there's no point on the string that's moving left or right. The points on the string are just moving up and down. So the linear density in the x direction stays the same. So as this thing stretches, if this maps onto that segment right there, yeah, the string has stretched some, but the mass is still the same, and the displacement in the x direction is still the same, and so dm dx is still uniform for that small little segment there. So I want to concentrate though on just, I'm going to take this small little element right here. It's going to have a slight curve to it. And so the mass of this little bit is dm. And we can go for the bold visual effects, or potentially not so bold, depends on how well, seems to show up well enough. Those are supposed to be horizontal. So we'll have some tension acting down there at some angle theta. And over here, the tension is going to be slightly different. So it's just going to be the tension plus some differential in the tension. And the angle here will be theta plus some differential in the angle. The thing has to accelerate. There has to be some difference in the forces there and the angle. And so if we did a force diagram of this piece, I will have Ft cosine theta acting to the left, Ft sine theta acting down, Ft plus dft sine theta plus d theta acting up, Ft plus dft times the cosine of theta plus d theta acting to the right. We already have a coordinate system already set up here, which is good that I broke it up using that coordinate system. So now we do equations of motion. What are the two equations of motion for my little piece of string here?
T plus dft cosine of theta plus d theta minus ft cosine theta is equal to, I'm not sure.
Anyone want to help her out? What is the acceleration horizontally? dm times 0 officially. Vertically, there is acceleration. But, all right, so vertically, what's my equation?
ft plus dft sine theta plus d theta minus ft sine theta. Is it MA?
Yep, MA, dm.
dm.
A. Now, we've got this pesky cosine of theta plus d theta, which is not necessarily easy to work with. And so we need to somehow resolve that. So let's resolve it. So if I did a plot of theta versus cosine theta, and I have some value of theta here, which corresponds to some value of cosine theta there. And then I have infinitesimally far away, but theta plus d theta here, which corresponds to cosine of theta plus d theta. So I just have these 2 points on the curve where the abscissa is separated by some value of d theta, and the ordinate, abscissa, ordinate is separated by whatever that difference is. If I look at the slope between these 2 points, and in essence, this is how when you're starting derivatives, this is how you find the derivative. You just let d theta go to 0. But the slope there, we can find 2 different ways. Way number 1 is rise over run. Cosine of theta plus d theta minus cosine of theta divided by, might change this way, theta plus d theta minus theta. Or it's just the derivative. So this is the derivative of cosine theta, d theta. So slope 2 different ways. If the denominator, we can simplify that. And over here on the right-hand side, that's the derivative of cosine theta with respect to theta, which is?
The derivative of cosine theta?
Yep.
Negative sine theta.
And so on the right-hand side, we have cosine of theta plus d theta minus cosine of theta over d theta. Now, ultimately, we're trying to figure out what cosine theta plus d theta is, this bit right here. And so we'll solve for it. And so we end up with cosine of theta plus d theta just equal to, well, multiply both sides by d theta, and then add cosine. So this is equal to cosine of theta plus, that's a negative there, minus sine theta d theta. If you will recall, this is pretty much how you do propagation of error also. Sine of theta, we're going to go through a similar process. It's going to obviously come out with something slightly different. And that is a sad marker. Less sad. So if that's my theta axis and my sine of theta axis, curve's basically looking like that. I have some value of theta here, some theta plus d theta there. This corresponds to sine of theta and sine of theta plus d theta. For the math purists in the group, presumably this is bothering you somehow, because I have a theta axis and then I have a specific value of theta here, or I have a sine axis and then I have a sine value here. This is a specific value of sine, and this is a general value for sine. Mathematicians generally don't like that, and so they put in primes and subscripts just to differentiate. In physics, we know what's going on, so we don't need to do that. You're just supposed to know. So we're going to go through the process again, that the slope is rise over run, so sine of theta plus d theta, minus sine of theta, so the rise. And then the run is just d theta. Skip the step there. And that's just equal to the derivative of sine of theta, d theta, which is so we can now solve for this sine of theta plus d theta by multiplying both sides by d theta, and then adding sine. And so this piece right here is just the sine of theta plus cosine of theta d theta. We can do one other bit here before we get too far. This acceleration here, that acceleration is vertical. It is the second derivative of the position in the y direction. So this becomes dm times the second derivative of y with respect to time. Questions to hear?
Can you repeat the what you just wrote?
This acceleration is vertical.
Oh, okay.
And so that's why, since I chose y as the vertical variable, that's why it's second derivative of y. Okay. I assume you're nodding, so that's why I sort of started skipping words.
Sorry?
I got the impression that you caught on what I was saying.
Yeah.
Okay. All right, so let's see, I need some room here, so I gotta erase something. All right, so from that first equation right there, what I have now is I have two binomials that I'm multiplying together, so let's FOIL. So I have ft cosine theta minus ft sine theta d theta, and then plus cosine theta dft minus sine theta d theta dft. So that is the product of these two binomials. And let me double check because I'd much rather catch my errors here than later. It's feeling good. Minus ft cosine theta equals 0. And now let's get rid of stuff. Well, there's an obvious thing we can get rid of. We've got have an ft cosine theta here and a negative ft cosine theta there, so those go away. We can actually get rid of one more thing here. Remember that the differentials are small. They're infinitesimally small. Well, right here, I'm multiplying two infinitesimally small things. So whatever d theta and dft are, if I multiply them together, I have something so incredibly small, this whole term is close enough to 0. Especially since you're multiplying by something that is no bigger than 1. And so what this has now been reduced to, if I just add this term to the other side, I have cosine theta dft equals the tension times the sine of theta d theta. And because I know how we'll be using that later, dft is the tension of sine theta d theta over cosine theta. And I'm going to leave it as sine over cosine instead of using tangent, just because it's going to be a little bit simpler later on to keep it like that.
How do you cosinus theta plus d theta, how you find that equation up there and?
This right here?
Or the other one down there, yeah.
That's the part that I just erased.
Okay, no, I have it here, the slope. How you calculated the slope is straightforward.
Right, yeah, I just basically found the slope two different ways, one using calculus and one using algebra. Set them equal to each other. Because the slope,
Because I thought, okay, but one was the slope for the sinus and one for the cosinus, no?
right, yes. So the one for cosine led us to this, and the one for sine led us to this.
Okay, the slope for the cosinus is minus sinus.
Wait, say that again?
The slope for the cosinus was minus sinus theta.
Are you saying that the slope of the cosine would have been a negative value?
Yeah, no, it's not that. I just trying to figure out cosinus of that thing, how I jump to the other. You just have it like transforming that like an equation of a line, something like that.
I'm not following what the issue is. That for the cosine, we picked 2 points.
Yeah, no, I know
Okay.
what you did, and it's perfect.
Okay.
I have no objection about the slope. But from the slope, how you do that cosinus give you that formula over there.
This formula here,
Mhm.
okay? You're asking how we get these equal to each other?
Mm-hmm.
Oh, okay. So if that point there is theta, and that's cosine of theta,
Uh-huh.
and that's theta plus d theta, so they're just some infinitesimal distance apart.
Uh-huh.
That would correspond to cosine of theta plus d theta.
Yes.
So cosine of theta plus d theta minus cosine of theta equals theta plus d theta.
Yeah, okay, and you just take it off. Sorry, I'm stupid.
Okay,
Okay.
you're back? All right.
Yeah.
Other questions at this point? All right, so now, we'll do something similar over here. We're gonna go ahead and multiply these two binomials against each other. So I have ft sine theta plus ft cosine theta d theta plus sine theta dft plus cosine theta d theta dft minus, again, that's product of foiling the binomials, minus ft sine theta is equal to dm times d squared y dt squared. Very similar to what we just did. We're gonna get rid of some stuff. So ft sine theta shows up here, and then I got the negative right there, so those go away. We have the product of two infinitesimally small values, so this whole term right here is approximately equal to 0. And so now I have this, what's left over. Ft cosine theta d theta plus sine theta d ft is equal to dm d squared y dt squared. Since from the first equation I have a value for dft, I'm going to go ahead and plug that in for dft here. So I have ft cosine theta d theta plus sine squared, I'll go ahead and do better than that. So ft sine squared theta over cosine theta d theta is equal to dm d squared y dt squared. I can now factor over here on the left-hand side. I do have some common things involved. I have ft d theta. So I'm going to factor that out on the left-hand side. And I'm left with cosine theta plus sine squared theta over cosine theta. And that'll be equal to dm d squared y dt squared. I've got a nice little fraction here within the parentheses as one of the terms in the parentheses. And so let's go ahead and add these together by getting the common denominator. Obviously, the common denominator is cosine of theta. So I'll multiply the left one by cosine of theta over cosine of theta. When I add them together in my numerator, I get cosine squared plus sine squared, which is 1. And so now I'm left with the tension times d theta times 1 over cosine of theta equals dm d squared y dt squared. And so we're almost there. Have to do a little derivative of an arctan. Nothing you guys can't handle. Especially if we do it the physics way. And how do you find the derivative of arctan of theta the physics way? You look it up. All right, so let's figure out why on earth we need that. Because I've got this d theta here and a cosine theta. We need to somehow deal with that. So as I look at this point right here, I have some dx value there. I have some dy value there. This angle right here is theta. Or I can do it from this over here if you want. That angle there is theta. It's supposed to be horizontal. There is a little bit right there, but that basically is an infinitesimally small change of an infinitesimally small value. Be like it's dy. In other words, it's insignificant enough that I'm going to ignore that tiny little bit there. And I'm looking at a triangle, a right triangle, where this is dx, this is dy, this is theta. My hypotenuse is dx, square root of dx squared plus dy squared. So I have tangent of theta is dy over dx. And so theta is the arctan of dy over dx. And I have a d theta here, and that's why we need to deal with it. So, if P is equal to the arctan of Q, what is dP dx? Anyone happen to know? That's what the website said, so I'm going with it. It also works. So given my value of q is dy dx here. So d theta dx is going to be equal to 1 over 1 minus dy dx squared, wait, no, plus, 1 plus, times d dx of dy dx. Make that a little bit better. D dx of dy dx, which is 1 over 1 plus dy over dx squared times the second derivative of y with respect to x. Also from this triangle here, I can find the value of cosine theta. Cosine of theta is just going to be dx over the hypotenuse of square root of dx squared plus dy squared. If I factor a dx squared out here, so this becomes dx over the square root of dx squared times the square root of 1 plus dy squared over dx squared. Well, those cancel out. And we're left with 1 over the square root of 1 plus dy dx squared. Hey, what a coincidence. That kind of looks like what we have over there, except without the square root. We gotta do one other thing and then we're ready for substitution. Questions up to here before we get back to our equation? So I'm going to divide both sides by dx because I have a formula for d theta dx. And dn dx, well, that's just my linear density. So this equation now becomes the tension times d theta dx, right here. That's 1 over 1 plus dy dx squared times d squared y dx squared times 1 over cosine of theta. Well, cosine theta is equal to this, so 1 over it is just the reciprocal. So that's times the square root of 1 plus dy dx squared is equal to my linear density times d squared y dt squared. We can do some simplifying here. The square root of this term right here divided by that term right there is just 1 over the square root of it. In other words, we get the tension times 1 over the square root of 1 plus dy. Like my handwriting is getting worse and worse. Try that again. I have tension times 1 over the square root of 1 plus dy over dx squared times d squared y over dx squared equals mu d squared y over dt squared. This right here is just the cosine of theta. So I have ft cosine of theta times d squared y dx squared is equal to mu d squared y over dt squared. Couple steps to go, we're almost there. We've used that already. I want to get this d squared y dx squared over to the other side, and I want to bring mu over onto the left side. So basically I'm bringing mu over here, and I'm bringing that over to there. So I have ft cosine theta over mu equals d squared y dt squared divided by d squared y dx squared. Remember that the dt squared is just dt times dt. It's the notation, you don't put parentheses around the dt, but it's supposed to be understood. So my dy's are going to cancel out. What I'm left with is dx squared over dt squared, which is just dx over dt squared. And dx dt is how fast this thing is traveling to the left, or right, as you kids today say. And that's the speed of the wave squared. So the speed of that little chunk right there is the square root of ft cosine theta over mu. But when we're really talking about a wave, what we're talking about really is the speed at this point. You can do it from a different perspective. So from the lab frame, it's going that way, but from the rope frame, the rope is traveling in the opposite direction. Sorry, from the wave frame, the rope is traveling in the opposite direction. So what I care about is at the top here, when theta is so close to 0, that this becomes the square root of ft over mu. And that is the speed of a wave on the string. Now there are 2 videos where I go through the derivation different ways. There's several ways of doing it. This is just the newest way I have discovered. And so if you have a standing wave like you do in the lab, then that would also be equal to the frequency times the wavelength, and the rest is just epic lab. Questions?
You need a bigger blackboard.
Yep.